welcome to the last two lectures of the mining and mechanical and electrical resistance of mining machines. So, the 59 and 60 lectures, this will be the last two lectures of this series. So, we will discuss about what is power electronics. We have discussed about what is a power system, what is a distribution system, transformers, induction motors, then we discussed about cables, we also discussed batteries. Now, you will talk about power control. So, when it is talking about control, generally all controls are done by computers, all digital control nowadays. So, in the digital control, everything is low power, low voltage. Therefore, it is called power and electronics. So, we will discuss the concept, what are the devices which are used to do the power control and what are the topology or what are the circuits which are made out of these devices. Those are controlled and uncontrolled rectifiers, inverters, choppers, etc. So, if you look at this, we have a motor which is having a moment of inertia J, it is driving and it is developing a electromagnetic torque. There is a 3-phase voltage supply VA, VB, VC and it does currents IA, IB, IC. And by the way, let us say it is an induction motor, it develops a torque T and it drives a load and leads the opposite torque of load is TL and it has a moment of inertia J and a friction coefficient B and operates at a omega radian per second. If you see the dynamic equation, what is that? J d omega v dt is the torque because of inertia torque, b omega is the friction torque which is equal to the electromagnetic torque developed minus the load torque. If electromagnetic torque is more than load torque, it will accelerate. If it is less than load torque, it will decelerate. If they are equal, then there will be no acceleration, deceleration, etc. So, if you look at this, so you can, it seems by you do not have any control on the load torque because that is the demand of the work. For example, there is excavation. So, the excavator does the excavation, that has particular demand, you have no control over that. If you have a conveyor, the conveyor belt has to drive the material from one place to other, no control over that. So, what you can control? You can only control the electromagnetic torque. So, how can you control the electromagnetic torque and speed? By controlling the voltage here, current here and also the frequency of supply, So, by means of that you can have speed control or you can have torque control. So, by direct torque control you can DTC, which is very familiar nowadays, you can control the torque and the speed, you can also do speed control indirectly. So, this is required for many applications. As I said, this is one of the drives where you need variable frequency operation. As you can see here, you need to change the speed. So, there are dampers, here there is excavation is going on. So, there is lighting. So, everywhere you need control and also there is solar cell where you need to convert the solar energy into electrical energy by means of photovoltaic cells, and photovoltaic cells again needs converters, etc. So, for all these regions you need power control and this is done by power electronics, that is the branch. So, we will talk about power electronics now. So, what are the key applications? Conveyor drives, there are conveyor belts which are need the speed and torque has to be controlled, hoists and elevators, ventilation fans, battery powered mining vehicles and crushers and mills. So, these are different key applications of power electronics or speed control where you need to do power control. You need, and how you do it? By power electronics or converters, we call it converters, power converters, which can be AC to DC and it can be DC to AC also, it can be DC to DC, it can be AC to AC. AC to DC is known as rectifiers, DC to AC is known as inverters, DC to DC are sometimes known as choppers or They are also known as buck converters, BUCK, boost converters, buck boost converters, sometimes Cook converters. So, these are different converters for DC to DC, and AC to AC generally very rarely used, they are known as cyclo converters. That means from a fixed source you can generate variable DC, from a fixed DC you can generate variable AC. Similarly, from fixed DC you can generate variable DC at different voltage level. Similarly, from fixed AC you can generate variable AC. So, right hand side is variable, this side is fixed. So, this side is fixed supply, this side is variable supply. So, how to vary? By doing some switching of power converters. So, this you are going to see in power electronics. So, what are the challenges if you want to do power electronic control etc. on the surface? Fine, but inside the mines there are lots of challenges, because the control electronics and power electronics both have to tolerate dust, moisture and vibration. Second, it is explosive environment, because if there is anything wrong, any gas is created because of some short circuit, it becomes explosive. Then power demand is not small, it is high power, because you have to go underground, you have to operate things. Then there is EMI EMC issue because of long cable lines. So, these are the problems and issues which has to be countered to design power electronic control converters. This is clear. So, there are many challenges and issues. So, before that, to get into power electronics, we have to understand what are the power semiconductor devices which can be controlled by electronics. So, these are the power semiconductor devices, that means high power semiconductor. You have heard about low power semiconductor like IC chips, computers, laptops, etc., embedded systems, telephones, but these are semiconductor devices with power capability. So, you can see here there are some diodes like this, you see diodes, they are called diodes. Diode, you must have heard about diodes, but they are power diodes, not signal. It is a huge one. Power BJTs, bipolar junction transistors, not so popular, but diodes are there. MOSFETs, power MOSFETs, they are called power MOSFETs, not ordinary MOSFETs. Similarly, IGBTs, insulated gate bipolar transistors, insulated gate. So, this is known as insulated gate bipolar transistors, insulated gate bipolar transistors. These are bipolar junction transistors. They are very popular earlier, but for power transistors you can always write power. So, they are now outdated, but this is the new thing which is known as gallium nitride or silicon carbide. This is called silicon carbide devices. These are just silicon devices, only silicon, not germanium, but this is silicon carbide bonded together, which increases the breakdown voltage, makes it faster, better thermal conductors. So, this is why this is nowadays very much preferred. These power MOSFET etc. are actually designed. You can say SiC diodes, SiC MOSFETs. So, these are now becoming very popular. So, these are power semiconductor devices, as you can see here. So, these are switching, that means you have to make it on and off continuously by use of a gate. You see there are three things here, one is the gate, one is the drain, one is the source. By using gate you can control it. So, by controlling you can control the voltage frequency by switching, controlling the switching. So, you can see, let us get into the first thing is power diodes. Power diodes, as you know, they are p-n junctions. You can see there is a p and there is a n. N is actually graded. This is higher n concentration. N means the semiconductor has a p type semiconductor and n type. P type semiconductors are basically holes and these are electrons. These are called intrinsic carriers, intrinsic carriers. So, p types are holes, they move, or n type. So, there are two types of material, p type material and n type material. Yes, semiconductor device, you must have done it in your physics. Just recapitulate otherwise what is p type, n type. So, this p type material is here, then n type. So, this is anode, this is cathode. So, if you make it positive and here negative, the current will flow, but if you do the reverse, current will not flow. So, these are called power control, and there is no control here. So, if you make it positive, only control is, that means if you make anode positive, you can see V is positive, after a threshold this start conducting. That means if you apply, the symbol is like this. If you apply in a circuit, suppose you put it in a circuit, if it is positive, this will, and this voltage across this diode Vd, you can see this is Vd and this is I, this is plus, this is minus, and this is current I. So, this Vi characteristic like this. If you keep on increasing this voltage, suppose this voltage is variable. So, if you keep on increasing the voltage, then after some time it will start conducting depending upon this resistance. If you keep on increasing, the current will keep on increasing. Okay. And in the reverse direction, suppose you make it negative, it will not conduct till breakdown. So, this is very high, this is very high. You should make a discontinuous here, so that actually this axis, this point is very large. So, this is called breakdown voltage. After breakdown, it becomes short circuit, but this voltage is normally many times, 100 times or 200 times more than this voltage. This is called knee voltage or caught in voltage. This is called breakdown voltage. So, in this circuit, if you make the voltage negative, after this breakdown voltage, it will conduct. And that what you see in the right hand side diagram is called the reverse recovery. That means when you make, suppose you have a diode here and there is a resistance here, and if you supply a AC voltage here plus minus. So, when it is plus with respect to this, it will conduct, but the moment it reverses, it will stop. While stopping, this term of there is some charge, because this is a PN junction, the charge has to be swept aside. So, that means when you make it plus minus, it will start conducting, but just you make plus minus reverse by this AC source, this will stop conducting. While stopping conducting, the charge in this layer has to be swept across, and there is a spike current in the negative direction, and it is called, this whole process is known as, this is reverse recovery time, and this is turn off mechanism. So, this is power diodes. So, these are the power diodes. You can use power diodes for rectification. So, how do you do rectification? So, if you have a, if you have a AC source, if you give a diode like this and here is a resistance, so this becomes a half wave rectifier. How? So, that means AC source, this is resistance, this is the diode. So, AC source voltage will be like this, this is the AC source voltage. Then what will happen to this diode? Whenever this is positive, this is Vs, let us say Vs. So, the diode will conduct when so the diode will conduct only in the positive half, because this will become positive. In the negative half, the diode will stop conduction, again positive half. So, like this, if you see the diode output voltage, this will become like half wave rectifier. That means DC only half waves are there. So, it will find it is half wave, and if you put a capacitor here, this becomes very smooth like this. So, this becomes DC. So, this is half wave rectifier, AC to DC. You can also have a full wave. How to have a full wave? So, what you can do is, let me draw it again here. So, if you draw it, you see this becomes, suppose I have a diode arrangement like this. And you have plus minus this is diode D1, D2, D3, D4, this is resistance R, this is VST. So, you can, if you draw this VST which is like a sinusoidal wave, this is VST, what happens to the V here, this voltage V, this is the V output, let us say. So, in the positive half cycle, this diode, this is positive, this is negative. So, this diode will conduct, also this diode will conduct, because this will be the path. So, this will be the path. In the positive half cycle, this will be the path, because this will be positive. So, this path is the positive half cycle, and voltage will be these two. So, voltage will be, this one is the positive half cycle voltage in the output. Now, what happened in the negative half? In the negative half, what happens? In the negative half, this becomes positive and this becomes negative. So, once this becomes positive, so the path becomes, this becomes forward biased, then there it goes like this, comes back like this, then comes back like this, comes back like this, this complete the circuit. Again this one becomes connected to this. So, again this one will just flip and this will become, so it will keep on. So, this becomes a full wave rectifier, it is a full wave rectifier FWR, and if you put a capacitor here, this rectification filters out, that means it will go like this. So, this is called full wave rectification, full wave rectifier, but you cannot control it, only the AC to DC is happening, AC to DC. This is full wave rectifier. So, it is can be written like a bridge circuit. So, this is full wave rectifier. So, there are different kinds of diodes. One type of diodes are semiconductor, one type of diodes are Schottky diodes, where there is a metal and there is a N type material, they are joined together. So, this metal and N type material makes the Schottky diagram. So, this metal and the junction is metal and N type. So, this is electrons, lot of electron, this is also some electron. So, these are known as Schottky, they are very fast diodes and very fast recovery time. They are normally not used as power diodes. So, this is about diodes. Now, let us get into BJTs. What is BJT? BJT is called a bipolar junction transistor. BJT, bipolar junction transistor, BJT. Okay. So, how does it look like? You can see this look like NPN or PNP, two types, NPN, N material, P material, N material, and there is a base here and there is collector and there is a emitter, collector, emitter, base. So, you can say collector, this is emitter, there is a base. So, you can say like that, collector, emitter, base. So, collector, emitter, base, this is base, this is collector, this may be emitter, this is collector, this may be emitter, this is base. So, this is how it is done, collector, emitter, base. So, this is junction, collector, base junction, this is collector, emitter, junction. So, emitter. So, the symbol is like this, collector, emitter and base. So, what happens? By this, you look at this circuit, this is known as a bias circuit. By injecting current into the base region, you can connect the collector and emitter. By controlling the base, controlling from base, you can switch it on or switch it off. That means, if you have a full base drive here, this will be shorted and the voltage across this will be very small and transistor will be on. That means, this battery voltage will come here. But again, if you make the base current 0 or negative, this will be open. That means, it is behave like a switch. If this is the DC battery, you know, if you just make it as a switch. This is the resistance you can say. So, this is your BJT, this switch is your BJT, which is controlled by base. This is collector, this is emitter. So, this is the voltage supply, voltage R, let us say. So, if you give the base signal, this will shorted, that means V will appear here. If you remove it, it will be open. So, that means if you supply and VB, you supply sometimes, make it on and then off, then on, again off. So, what happens? The output voltage also becomes on and off. The output voltage also becomes on and off. You can see the output voltage become on, then 0, then on, then 0, and if you make it a capacitor, this voltage can become very smooth. But what will happen? If you increase the off time, the voltage will also reduce. That means the average output voltage will depend upon the duty ratio. Duty ratio is called T on divided by T on plus T off. That is the transistor on off time. So, this duty ratio D. So, average voltage in the output, that means the output voltage V output, if this is fixed, then V output will depend upon the average voltage is equal to the duty ratio into the V input. Because you see, if it is on and off, if you take the average voltage, if this is T on, so this is T off, and total time from here to here is T. So, the voltage across this average voltage, because will be equal to T on by T into the voltage supply. So, which is this is called the duty ratio. So, by changing on and off time, you can adjust this, and if you put a capacitor across this, it will be also filtered, it will become smooth, and you can control by switching on. That means the base input here you can switch on by switch off by a low power electronics. So, this is first is the control, but BJT is not used because of lot of heat current control, and this is the BJT characteristic. So, this is the collector to emitter voltage, that is voltage across collector and emitter. This is the BJT symbol, base, this is collector, this is emitter, this is NPN, this arrow means this is N, this is P, this is N. So, this is NPN transistor. By controlling this, so this is VCE, output voltage VCE, and this is the current IC, and this is current IB. By different current IB, you see increasing, the IC VC relationship looks like this. Okay, so this is called the output characteristic of the transistor. So, I can either work on maximum IB, this is IB changing, this is IB changing. So, if we keep on changing IB, it will operate, it can operate here or here. That means here it is completely on, IC is maximum, current through this, and voltage is minimum, and this is called on condition, and this is called off condition. And this is possible to move along this line by controlling this IB. And this line is what? This line is VC, V out, this voltage V minus IC into RC is equal to VCE. This is the line. So, this line gives you the, this is called load line, and this is the transistor characteristic. Wherever they intersect, they operate there. So, if you make IB 0, it will come here, if you make IB maximum, it will come here. So, you can operate between these two, switch on and off. So, these are BJTs. So, you can see the same BJT expanded a little bit here, the same thing becomes NPN type BJT or PNP type BJT. Then there is a load line, this is the circuit which I just discussed right now. But this is not used nowadays, this is almost outdated. The reason is heat and the control, which needs lot of current. For base current needs high base current for control. So, that is ruled out. So, therefore, it is not much used. So, we have to move to the next good device, that is called a MOSFET. BJT is not used, mostly obsolete in drives, slow switching, high base current. So, as I said, base current requirement is high. So, we will switch to MOSFETs. MOSFET is called metal oxide semiconductor field effect transistor. Metal oxide, this is metal oxide gate, it is insulated gate, it is not connected to the semiconductor. Source is connected. So, there will be a drain, there will be one source. This is called drain, there is a mistake here. So, what is happening? That means you can apply a voltage between these two, and when you switch on gate, what will happen? This N plus will become connected, because this will become very high concentration. So, the opposite also is true. Okay. So, therefore, by controlling the gate voltage, you can control this channel, and this channel will either short circuit or it will be open circuit. So, this is the principle of operation of MOSFET. Little deep dive. So, this is the MOSFET, as you can see. There is a gate source, not this one. This will be gate source, this will be drain. This will be drain. So, this is the look like your MOSFET. So, this MOSFET symbol is something like this. This is the gate, and this is substrate, this is substrate. This is your source, this is your drain. Just like BJT collector emitter, this is source drain, and since it is substrate is negative N, so we like put the arrow like this. This is a MOSFET. By applying a suitable voltage, so here gate to drain, if you VGS go to source voltage, let us say this is drain, this is generally source, opposite. So, if you apply here also drain, this is source. By applying a positive voltage here, you see you are able to attract electrons here. So, what will happen? This electron will take a path here, because the electrons more. So, this will become a continuous path. This electron will come here and finally it conducts. So, applying a positive voltage VGS more than a threshold, this conducts. Once this conducts, so this is shorted. This is like a switch, and you show MOSFET can be also used like a switch. So, control switch depending upon the gate. So, MOSFET symbol you can write like this. This is your drain, this is the source, this is the gate. So, by proper gate you can close or open. So, MOSFET is also can be used as a switch. So, this is particularly used in high frequency applications, very high frequency applications, but low voltage, high frequency and low voltage applications. Then we go to next is IGBTs. IGBT. What is IGBT? This is called insulated gate bipolar transistor. It has got good properties of transistor as well as MOSFET. So, what is the bad property of transistor? It needs more base current. What is the good property of this MOSFET? It needs very less gate current, because it is insulated. You see, this is insulated. The same thing here. So, there will be insulated gate, but it will behave like a transistor. Transistors are good because they offer very quick turn on, also high current. So, the insulated gate bipolar transistor looks like this, as you can see here. If you go there, so it is a combination of MOS plus BJT. So, this is how the symbol is. You can see there is a MOS plus BJT. So, it is a parallel anti-parallel diode. So, you can say this particular IGBT can be used like a switch with a anti-parallel diode. This is IGBT. So, there are now IGBT modules. That means, in one module there could be few IGBTs. So, it has a gate, it has a emitter and collector, unlike the MOSFETs where there is a drain and source, but here it is emitter and collector, just like your transistors, but there is a gate here which is insulated gate. That means, you need not have lot of voltage here to make it on. So, the equivalent circuit of an IGBT with all parasitic inductance etc. comes like this. Collector 2, there will be a small inductance, there is a parasitic capacitance, there is a anti-parallel diode. So, there is some inductance parasitic. So, this is all about IGBT. So, this can be used like a switch, and the switch has a. So, this can be used for mostly for inverter. I will tell you one single phase, one inductor, so inverter. So, you can see This is the switch IGBTs I will use. And I will put my load here. This is your transistor 1, transistor 2, transistor 3, transistor 4. So, these are the two terminals of the output. Suppose you put 1 and 2, the voltage across this load VL, if this is E, then VL will become E. If you switch on 1 and 2 IGBT. So, they are all connected with anti-parallel diodes. So, this is 1 and 2. Similarly, if you switch 3 and 4, so VL will become minus E. This is 3 and 4, this and this. So, if it is this and this, so this voltage is connected here, this voltage is connected here. So, minus E. So, that means in one cycle you can get plus E, then minus E, again plus E and minus. So, this becomes AC. So, this is an DC to AC converter, which are known as inverters, IGBT inverters. By properly filtering this, you can achieve very good signs, almost smooth transition by filtering. Okay. So, IGBT can be used as also a switch. So, we will stop here, again we will go to the next lecture.